Well, thank you for inviting me to talk. So for the next two lectures, we're going to be looking at the physics of sensory systems. So we're going to be looking at vision and hearing. With any physiological measurements, the starting point is to understand the anatomy and the physiology, which is then key to interpreting any data that you collect. With sensory function, the brain's understanding of the outside world really comes from the sensory inputs it gets from a range of senses. And it takes these inputs and rationalizes them and then tries to make sense of what's going on. And to achieve that, the body's got a range of modified cells that detect some part of the environment. So in the case of vision, we're actually detecting electromagnetic radiation. And we're detecting it in quite a narrow band of frequency or wavelength. And that's what's known as the visible light spectrum. Now, in order to see or detect that light, we first have to present it to the receptors in the most efficient way. So starting from the outside in, initially we've got the eyelids and the lacrimal system, which basically do the housekeeping of the front of the eye. They keep it moist, they keep it clean. If there's any problems with this system, the eye can dry out, it can start to get ulcerated, the optics can degrade, and then that will then affect the visual ability. Behind that, we have the cornea. The cornea is a transparent layer that effectively bends the light to focus into the back of the eye. Now again, this can go wrong if it gets ulcerated, if it gets scratched, if it gets opaque, or if it's the wrong shape. All of that can give distortion or reduce the clarity of the image that we can see. Behind the cornea, there's a little chamber that's filled with fluid, and this fluid is continually made and drained. And if the fluid pressure starts to go up, we can then get glaucoma, which can affect vision. Behind that, we have the iris, which controls the pupil, and this modulates the amount of light entering the eye. So when we go into the dark, the pupil opens. When we go into the bright light, it closes. If that wasn't working properly, then the image that we see would either be overexposed or underexposed. We then have the lens, which fine-tunes the focus of the rays onto the retina. And behind that, there's the vitreous, which is basically a clear sac filled with jelly that becomes more fluid-like as we get older. Now, all of these parts together form the optics of the eye, and they're purely to allow the light rays to hit the photoreceptors at the back optimally. If they aren't working properly, either they can focus too far back and we end up being long-sighted, and that can be corrected optically with the convex lens, or alternatively, if the power is wrong, we can be short-sighted. And again, that can be corrected using a concave lens. So any problems with the optics can be addressed optically. When that light then arrives at the back of the eye, we have this layer, which is where the photoreception happens. And this layer is incredibly thin. There's some thicknesses up the top there, and it's quite complex. So we've got photoreceptors where the light's detected. They then feed the signals through this whole array of cells that act like logic gates until it arrives at the ganglion cells, and the ganglion cells then generate the signal that passes down the nerve to the brain. So the retina actually detects the light and starts to pre-process the information. It's actually neural tissue at the back of the eye. So that detector is covered in a photosensitive pigment. So when light hits it, hopefully it's detected and generates a signal. But there's a chance that the photon could miss the chemical. So the way the eye addresses that is the photoreceptors have a whole stack of discs, all of them coated in the chemical. So if it misses a surface, hopefully it will eventually hit one, and then we'll see that photon of light. And because we've got a matrix of those at the back of the eye, whenever light enters the eye in a straight line, the brain can work out where that light came from. And so that helps the resolution. Now, one issue is if the photon misses all of those discs, it might well hit the back of the eye and bounce. And if that were to happen, the brain wouldn't know whether that photon was entering the eye or leaving it. And that would then degrade the image because it wouldn't know where that light came from. So as humans, the very back layer of the eye absorbs stray light. It doesn't allow it to bounce. And so that helps with our clarity of image. If you're a nocturnal animal, you can't afford to waste photons, So a nocturnal animal has a mirror surface at the back, and that does allow the light to bounce, which makes them better in low light levels, but it degrades the quality of the image that they can see. But that's why if you shine a light at, say, a cat at night, their eyes will glow, whereas humans will have dark eyes. And it's this very back layer, and a nocturnal animal is reflective, where ours is an absorber. Now, although I've shown it that the signal leaves the back of the eye in the same direction as the light, in truth, it works the opposite way around. So light enters from the front of the eye, passes through these cells to the detector. If the detector detects that light, the actual current flows towards the front of the eye to where the ganglion cells are, and then enters the nerve fibers. Now, in order to detect all of those wavelengths of light, we've got two major classes of photoreceptor, rods and cones. The rods work in very dim light, and these give you your night vision, and they tend to work in shades of grey. They're not chromatic. But then to pick up coloured light, we have the cones, and there's three types: short wavelength, medium wavelength, and long wavelength. And between the three, they will then give us all of the colours that we can perceive. There's far more rods than cones, but the cones are better in daylight or room light. The rods are better in very dim light. So if you can see in colour, you're using your cones. If you wake up in the middle of the night and look around your bedroom, you'll be using your rods. And also what changes is the relative density of these receptors across the retina. So the bit that you read with, the very centre of your retina, is pure cone. There's no night vision. And then as you move further out into the peripheral of your vision, the density of the cones get reduced and the density of the rods increase. But also what happens is in the centre of your vision, you've got very high sensitivity to detail. So your spatial frequency is high. And as you move further out, that spatial frequency gets worse. So your vision becomes more blurred in the periphery, but the nerve fiber diameter increases. So your peripheral vision is more sensitive to flicker or movement. So your peripheral vision warns you that there's something there, and you'll then target it with your central vision to get a good idea of what that image is. And the reason for that change is the way that these intermediate cells act as logic gates. So every nerve fiber is actually connected to a patch of retina. And you'll have retinal cells that excite that ganglion cell, surrounded by retinal cells that inhibit it. So if you put a uniform light in the center but not the surround, the ganglion cell will be happy. But if you give a patch of light over both center and surround, or darkness over both, it won't fire as well. So what the retina is doing is measuring relative light rather than absolute. Now actually, any given part of the retina, the photoreceptors can feed into multiple ganglion cells. And a given receptor, based on the logic gates in the middle, if you excite the receptor, might simultaneously excite one ganglion cell and inhibit another. And all of these patches overlap in the retina. And they will eventually feed to cells in the brain. And so this brain cell is looking at these ganglion cells, and these ganglion cells wants to see light in the middle. So effectively, this cortical cell is now an edge detector. It's looking for a line of a certain angle. So the retina builds up relative light, and the brain then takes these signals, and the separate parts of the brain that are interested in contrast, contour, phases, texture, color, monochromatic, depth, and they build the image up based on how the retina perceives relative light. So, demonstration. When we look at these two grey rings, the retina sees those two levels of grey and compares it to the background. So at the minute, you see the two rings as being the same density or brightness of grey. But if we change the background, the retina now sees this grey ring as being darker than that one because it's comparing it to what surrounds it. So this is happening in your retina. The retina is seeing these two greys as being different because there's a relative difference between the background. But the brain can then put context to that and step in. So if we take the same grey ring and put the same background in, the retina still sees these two greys as being different. But then the brain says, well, actually, this is a solid object. It's most likely to be the same grey. So the brain overrules the retina, and you see that as one grey image. But it doesn't take much to break that. So if we break that image into two, the retina will work, and this grey now appears darker than that grey. You're now using the retina As soon as they touch, the brain takes over and says, no, it's the same grey. In some circumstances, though, the brain and the retina can both get it wrong. So if we split them now in this direction, the retina sees this grey as being darker than that grey. The brain steps in and says, well, actually, I've got a dark loop interlaced with a light loop. So you're probably right. These two are different. So now these two greys look really different, even though they're the same. And to prove they're the same, if we slide them across, there's no difference. But in this situation, the retina sees the relative difference. The brain agrees with it, that the context fits. And so you can't really see this grey as being the same as that grey until we put the two together again. And then the brain realizes it's the same object. And so you perceive the same grey. Now, it seems a strange thing. Why would we want to measure relative light and not absolute light? It actually makes sense. So if we look at an object, say this black letter on a white background, it doesn't matter what the room light is, it will still look like a black letter on a white background because we're measuring the difference between the black and the white. So these parts of the retina won't be getting a very strong signal because they're fully illuminated. And these parts of the retina won't get a very strong signal. The ones that get the best signal are the ones that fall around the edge. And so one, you get an economy of signaling because all we do is signal where the edge is and then the brain fills the rest in. But also because we're now looking at that as a relative, black against white, whatever the room light condition is, from candlelight to bright sunlight, it will still look black on white. If we looked at absolute light, then the difference between the paper and the black would get progressively different in different room light conditions. And we also look at colour in the same way. We look at relative colour, not absolute. So when the retina then has decided what the world is happening in relative terms, it sends the signal down to the brain. And we've got a large part of the brain interested in vision. We're a very visual creature. So the whole of the back of the brain is vision. And the way that the brain is wired up, or the eyes are wired up to the brain, is not quite the same as the rest of the body. So the rest of the body, the right side of your body goes to the left side of the brain and vice versa. With vision, though, it's the right world goes to the left hemisphere and the left world goes to the right hemisphere. So half of each eye goes to half of each part of the brain. And that's useful to know because if anybody's got a problem with a retina or the nerve before this crossing, then the problem just exists in one eye's vision. If the problem occurs anywhere beyond that crossing, then the problem would occur in part of both eyes. And we can use that information to interpret results. So that's a whistle-stop tour of anatomy. So if we start to look at measurement, there are various measurements we can take, some subjective, some objective. Subjective measurements is where we ask the patient to tell us what they can perceive, what they hear, what they see, what they feel. And they give a value judgment. Objective measurements are more where we make a measurement where the patient doesn't need to tell us anything, but we can put a number to it. With the subjective measurements for vision, there's a number. We can look at visual acuity, so how good are they at picking up detail. We can look at accommodation, so how well can somebody see things as they get closer to them. And that ability declines as we get older. We have to hold things further away to focus. We can look at visual field, so how much of the world can they see? We can examine stereopsis, so are the two eyes working together to give them proper 3D vision? And we can also look at colour vision, and that's useful because although quite a few people are born with a colour vision defect, more common in males than females, if you acquire later a problem with colour vision, it can be the sign of a problem, either a problem with the retina or a problem with the nerve. So colour vision is useful to know about. So if we measure acuity, the one that you're most probably familiar with is the Snowman chart. And it's been around since the 1800s. And essentially, you're asking the patient to read what they can see on that chart, and the chart has got letters of decreasing size. There's quite a bit of science to it. It's actually calibrated to be looked at a certain distance. And 6 refers to 6 meters. Occasionally, you'll see it in 20. So 2020. That means it was in imperial measure in the 20th feet. So if you were to look at that chart at a 6 meter distance, and you could read the line that's one up from the bottom, you would get a value of 6.6. And what that means is that's average vision. What you can see at 6 meters, the average normal person would also be able to see at 6 meters. If you can read the very bottom line, it means you're better than average. So what you can read at 6 meters, the average normal person would have to bring it closer to 5 meters to see it. And then as you go further up the chart, your vision's getting worse. So if you can only read the top letter, what you can see at 6 meters, the average person would be able to see at 60 meters. So you're 10 times worse than average. And then if people can't read any of those letters, we then move on to count fingers. So if you hold your fingers up, can they count? Or if they can't count the fingers, can they see your hand moving? So it's hand movement. Or can they see you turn the lights on and off, light perception? Or can't they even tell that? No light perception. So that is the most common psychophysical test of visual acuity, but it's got its limitations. So if you notice, there's only one letter at the top, but there's multiple letters at the bottom. So you've only got one chance of getting the top line. Also, as the letters get of decreasing size, the gap between the letters stays uniform, and the gap between lines stays uniform. And actually with visual perception, there's a crowding effect. It should be scaled. Also with this test, the problem is you only get scored on a whole line. So if you manage to get some letters off the lower line, you won't get any marks for it. So what we tend to use clinically is what's called a logmar chart. So with this one, every line's got the same number of letters. Every space and gap is scaled on a logarithmic scale. So what this means is we can actually change the distance of the patient. If they can't see the top line, we can move them closer and adjust the score accordingly. And also every letter contributes to the score. So if you get, say, the 6-6 line, let's say the 638 line, and one or two letters below that, it will contribute to the score that you've got. One thing to bear in mind with the visual acuity, though, is our ability to read objects depends on the contrast. So the lower the contrast of the stimulus, the harder it is to see smaller items. So that's why most visual testing is done with a backlit screen in a dimmed room to raise the contrast level. But also, if you've got a patient with a visual abnormality like a cataract, what the cataract will effectively do is reduce their contrast. So even though your stimulus is really well lit, their optical disability lowers the contrast, which will make their acuity worse. So we have to consider that when we're making measurements. Visual field testing, as I said before, we present the patient with lights in different parts of the visual field. We ask them to respond, and the lights we present them with can be a different size and they can be a different brightness. And we can map out what each eye can see of the world. And from the patterns that we get, we can decide whether the abnormality is likely to be living in the eye, because maybe it affects one eye, or maybe there's a random pattern to the distribution, or if the defect is behind the chiasm, so it tends to affect both eyes, or in this particular case, this bitemporal, that's characteristic field loss of somebody with a pituitary tumour. So the pituitary gland, if it gets a tumour, will press on this chiasm, which stops the fibres from the nasal side of each eye going to the brain, and so they get a very characteristic visual field loss. So just a field loss like that will tell you what the problem is, without any further testing, really. Colour vision, number of ways we can do it. And essentially, we either ask the patient to look at objects that are designed so that only people with normal colour vision will see a certain response, or they're designed so that if you've got a colour defect, you'll see a particular response. Or we have more long-winded testing where the patient's asked to order different coloured objects into a specific order. And if you've got compromised colour vision, you'll find these tests difficult. And so that will then show you whether they've got a defect or not. And if they have got a defect, it'll show you what wavelengths of colour they're confusing. So that's some of the psychophysical tests that we can do. Also with ophthalmology, it's quite important to look in the eyes. So a classic way of doing that in the clinic is with a slit lamp, and it's essentially a microscope, binocular microscope. What's nice about the slit lamp, though, is the light source can be changed. So we can have spots of light, we can have slits of light of different length and thickness. We can put filters in to use different coloured light. And then also this light can rotate on the axis of the eye that we're looking at. And the eyepiece can rotate about the axis of the eye that we're looking at. And the two can be fixed together, so you can sweep the view and the light around the eye, or you can sweep the eyepiece around but keep the light fixed, or the opposite. And by combinations of these different mechanisms, it allows us to look at all of the different surfaces of the eye from the front right the way back to the retina. If we want to look in this angle, so this angle here in the eye can be a cause of glaucoma if it's too narrow. You can't actually see that from the outside because it's around a corner. So the medical use prisms, and they have a piece of glass that touches the front surface of the eye, which bends the light and allows them to see around that corner. So we can use prisms to look into the eye. Pupil responses are useful. The idea of the pupil response is when light goes into the eye, if the eye detects that light, it sends a signal down to the nerve to the brain to say, I've seen something. But also part of that signal goes into the brainstem, and that allows the pupils of both eyes to constrict or dilate. And it's a bit like an aperture in a digital camera. So if you shine a light in one eye, both pupils should constrict. And that tells you that the nerve is working from that eye, the brainstem is working properly, and the signal back to the muscles in each eye are working properly. So this is useful if you suspect a problem with one of the nerves, or if the patient is non-responsive, so they've been in a road accident. If you suspect there might be a problem with the brainstem, this will allow you to test that. If you shine a light into the eyes and the pupils don't respond, it's a worrying sign. And if neither eye works, it could be a problem with the brainstem. Structure, this one we'll do quite quick. There's lots of different investigations for structure. First one, we've said before that the curvature of the cornea can affect the clarity of the image that we see. And one way that we can test that, a very easy way, is to just have a disc with black and white disc circles on. Look at the image that forms on the front of the eye to see if they're symmetrical. And if there's any distortion in shape, we see this type of effect. Now, there are computerized versions now that actually give contour maps to show what the front surface is like. And that can account for any variation the patient might have in acuity or clarity. Tonometry, this is a technique where we can measure the pressure inside the eye. And for this one, we're looking for things like glaucoma. Two methods, there's contact, which is a bit more invasive, and we have a glass rod that touches the front surface of the eye, put anaesthetic in first. We also have a dye on the front surface of the eye. So when that glass rod touches the surface, it pushes the dye to the edge of the contact area. So then as we apply more pressure to that rod, it sequentially flattens more and more of the cornea. And so that then makes the disc of dye get bigger and bigger and bigger. And the idea is to look at how much pressure do we need to apply to make the disc of a certain diameter. And once we've got that, that can then be used to calculate the pressure inside the eye. Now in practice, that is quite tricky to measure from an operator side viewpoint. So the way we do it is actually introduce a prism into the device, which does that, it splits the image. So in this case, we're not putting enough pressure on. This case, there's too much pressure. When the pressure is just right, the two semicircles touch. So when those two touch, we can read the pressure off. And that's a far more accurate way of looking for that change than having a ring with a measuring device on it. So that way is the most accurate method, but it's the most invasive. So if you were to go to an optician, they would actually use a non-contact method. And with this one, we shine a light onto the front surface of the eye and measure the light that bounces off. Now you'll get the most light bouncing if the front of the cornea is flat. So what we do is we puff a jet of air onto the eye and we measure how much air pressure do we need to get the maximal light bouncing off. And then we can use that air pressure to work out the pressure inside. So in this case, there's not enough pressure. This case is too much. That's just right. So when we get the maximum amount of light reflected in, that means the cornea is at its flattest, so we can read this air pressure and work out what the fluid pressure is to cause that reflection. Fluorescent angiography, with this one we can look at blood supply to the eye. Blood enters the eye through a vessel that goes down the optic nerve, and it splits to supply the inner retinal layers, and then it comes into the inner surface, the outer and then the inner. And these are fed and drained at different times. So we can inject a dye into the patient's arm that fluoresces, and we start to take photographs with a filter in time, and we can measure, do these blood supplies come in and out of the eye at correct times? Do they stay in the vessels where they should be, or do they leak? And so that going tells us what the blood supply is like in the back of the eye. We can use ultrasound to look at structures. So the A scan sends a pencil beam in, and it measures the distance between different structures within the eye. Or we can take the beam and sweep it and actually look at internal structure, to look at things like retinal detachments or foreign objects. And then we've got the more traditional methods of structural analysis. So we've got OCT scanning, where we can use light beams to effectively give a cross-section of the retina. We can do CT scanning for looking at bony structures in the eye in the orbit. We can use MRI for looking at soft tissue. So these tend to be for things like bony growths that might be pressing the nerve, or there might be trauma that could affect the ocular cavity, or you might be trying to look for tumours that could be pressing on the nerve or the retina. So we have all the traditional scanning methods. And then we've got the bit that I'm responsible for. So I do evoke potential measurements. And what we're doing is we're actually stimulating the eye with light, and we're measuring the electrical signals that the eye or the brain creates in response. So we have calibrated light, either white light or patterned light. We then detect the signal using electrodes, and we use a differential amplifier, we filter it, we reject anything that's too large, and then we average it. So all of these techniques allow us to get tiny signals from the body. We're responsible for calibration to make sure the amount of light we're using is appropriate. And we can use that to look at room light or flashlights or lights on a pattern. And then we also calibrate the detecting or the recording device to make sure it's recording as we expect. So we can look at the filter characteristics, we can look at the linearity of the amplifiers, we can look at how well it rejects noise to make sure that the signals that we record are accurate and reproducible. And then we've got lots of different tests that we can do. So we can break the retina down into lots of different layers with different tests, even though it's a very thin part of the body. And then we've got different ways of looking at the brain. And together, or in combination, we'll use these tests to try and work out where the problem is, what the problem is, and how bad it is. So I'll just go through some of them quickly. With one test, the back of the eye, if it's working correctly, it generates a battery. And that battery varies with the room light. And so we can actually measure that just by using electrodes either side of the eye and asking the patient to move their eye left and right in the light and the dark. And so what we should see is in the dark, the signal gets smaller, in the light it gets bigger, and we can look at that to see how it's working. If you had a retinal problem in there, you wouldn't get this increase in the light. Also, we can take measurements from the back of the eye to flashing lights. And we have an electrode that actually touches the front surface of the eye. So we use a silver thread, but you can also use gold foil or contact lenses with a gold lip in. We dilate the pupil for nose tests, provide a stimulus, and record the signal that this detects. So with flashing lights, we can look at night vision if we darken up the eye, or we can look at day vision with light adapted, and you can see how small the signals are that we're looking at. So we're talking a few hundred microvolts. So we need really good conditions to get these signals away from noise. We can look at the macula, which is the part that we tend to use more for central vision. And again, we can actually break that down into different parts of the macula, either the bipolar cells or the ganglion cells, by looking at different components. And for that, we use a pattern stimulus. Or we can actually use a complex stimulus to break down the retina into all of these different parts. And then when we get to the brain, again, we can either provide moving checkerboards and get the signal from the brain, or if the patient can't fixate for us, we can use appearing checkerboards to record what the brain does. Or if the eye is full of blood or there's dense cataract, we can use flashlights and record what signal arrives at the brain. And then again, with this complex method, we can take a complex stimulus and we can break the brain response down into different regions, how well different parts of the nerve are working. So that's a whistle-stop tour of vision. So we start with the anatomy, we look at the physiology, and that then allows us to decide what tests to do, and then also how to interpret the results that we get from that.